In this video, we will be talking about exponential functions. So this is going to be chapter 4. The title is exponential and logarithmic functions, but we'll probably be talking about log functions in class. But this is going to be a little bit of exponential functions and how they work, what they look like, and a little bit of graphs as well. So generally, an exponential function has this following form. So it looks kind of like this. So let me go ahead and use the highlighter. So it has a form of f of x equals a b to the power of x. So it's very different than the way that we find many different types of functions. So we looked at polynomials that you have like a x to the power of n, and here n is an integer. It's a positive integer. And we've also looked at square root functions. We looked at rational functions. So rational functions is a polynomial divided by another polynomial. But now what's happening here is that exponential functions, they're a little different because now our x value, right, our x variable is now up on the sky. So it's now as an exponent. Here the x was not an exponent. So here x is the exponent. All right, so here a is a non-zero number and b is a positive real number not equal to 1. So this b value is always going to be some sort of positive real number that's something other than 1. So x is now on the power of the function. So that's one of the features of an exponential function. So the x is the power of the function. Okay, you don't have x squared. We got maybe 2 to the x. All right. So which of the following would be exponential functions? Okay. So what we're really looking for here is that we're looking for the x being on the exponent. All right. So here, this is a linear function. So this is not exponential. The x is not to the power. So this is linear, it's not exponential. Okay. Now let's look at this one. Okay, so now in this case, the x is up in the sky, is now an exponent. So this would be considered an exponential function. So this guy's exponential. All right, here it seems like we have a polynomial and a radical function. This is by no means an exponential function, so this is not exponential. And now we have this last one, pi. Pi is just a number, right? Like 3.14. And this is raised to the power of x minus 1. You can see that the x is on the numerator. I'm sorry, on the exponent. This will be considered an exponential function. All right. So to kind of make it a little clear, the x has to be in the exponent in order to be considered exponential. So how can we evaluate this? So let's say f of x equals 5, 3 to the power of x plus 1. Let's find f of 2. So all we really got to do is just plug in the 2. So f of 2 is equal to 5, 3, 2 plus 1. So remember, we had to use order of operation. So we first got to do the exponents. 5, 3 to the power of 3. We'll do 3 to the power of 3, which in that case will be 27. Right? And then we're just going to do 27 times 5, which is going to give me 135. So when x is equal to 2, my answer will be 135. And now one of the things that I want you to be very aware of is that usually exponential functions, when you start plugging in some numbers, they go crazy very easily. So if you plug in a number, they go really fast. So you can see just me plugging in a 2, this already went up to 135. So exponential functions are really fast. They're one of the faster functions. So be aware that plugging in a whole bunch of values can lead to really sharp curves. So let's talk about exponential growth and decay. And a lot of this is used in chemistry. You see a lot of half-lives and population growth, so bacteria And later on, we'll talk about pH, which will deal with more with logs. But exponential decay, especially with half-lives, are something that's used a lot in chemistry and also in physics. So you'll see a lot of this when you take your physics and chem classes if you haven't done so already. So exponential growth and decay. So a function that models exponential growth grows by a rate proportional to the present amount. So for any real number x and any positive real number a and b, such that b is not equal to 0, an exponential growth function has this form. Okay, so in this case, if my b value, okay, so this is exponential growth or decay. Now, how do we know if we have exponential growth or decay? Well, that will depend on what b is. So this b will determine if something's going to be exponential growth or decay. If my b is greater than 1, you got exponential growth. If your b value, though, is a number between 0 and 1, so some decimal between 0 and 1, this one experiences exponential decay. All right, so here I give you two different examples. So here is the function f of x equals 2 to the x. You can see that 2 is a number, is a b. The b is a thing that has the x. b in this case is greater than 1. So in this case it's 2. This guy will experience exponential growth. And you can see the features of this is that it's going increasingly really, really large. Okay, I plugged in a couple points here, and you can see that this is kind of what it looks like. In this case, this is the function g of x equals 1/2 to the x. You can see that this guy is also going downward at an exponential growth, but in this case, this guy is decaying. It's not growing. You can see that the b value, you can see it right there, our b value is equal to 1/2, which is a number between 0 and 1. So this one experiences exponential decay. So exponentially growing, like population, exponentially decaying, like maybe half-lives or something's dying. Okay, so these are two different types of problems. Now here are some of the highlights of these graphs. Okay, so the first thing is that you can see that both of them have the same domain. They're both negative infinity to positive infinity, because you can see that you can plug in any x value into these functions and you'll always get an answer, positive or negative. The range, you can see that the y values start at 0. Now, one of the things about these two different graphs is that they have exactly the same asymptote. So here you have a horizontal asymptote in both cases. So this one, these graphs are going to get really close to 0, but they're never going to touch it. So for exponential growth, you can see as x goes to the negative side, you can see that the y value is going to go to 0. This is the asymptote. So as x goes to the negative side, you can see that this guy is going to 0. And you can see that as x goes to the positive side for exponential growth, the y values go to 0. So that means that the horizontal asymptote will be at 0. And they always have that feature. Okay? So the graph will never touch the x-axis because no exponent will result as a 0. So if you kind of think about it, if you have y equals 2 to the x and you let y equal 0, well, there's no number that I can plug into the x so that I can get a 0. Because remember, 2 to the 0 power equals 1, not 0. Y equals 0 is a horizontal asymptote, which is what I just said. And the y-intercept is always at 1. So these guys, exponential growth or decay, no matter what it looks like, is always going to have a y-intercept of 0, 1. Always. Both of these guys, y-intercept is at 0, 1. So these are really good features because when we start graphing these guys, we're going to use the horizontal asymptote and the y-intercept and the shape of the graphs to be able to shift them as well. All right, so we'll be looking at that a little later. Okay, So these are just some highlights. So make sure that you know a little bit of the highlights, okay? So another note, so for exponential growth, as the b value increases, the growth becomes steeper. And for exponential decay, as the b value decreases, the decay becomes steeper. So what does that kind of mean? So if I have the graph of y equals 2 to the x, so let's say y equals 2 to the x looks like this. Y equals 2 to the x power. If I increase the value of b to maybe 3, the graph, what's happening is that this guy is going to go much faster. So it's going to go to infinity much faster. So this will be y equals 3 to the x. So these are kind of some of the features. The higher the value of b, the much faster it's going to go to infinity. And same thing happens with decay as b decreases, as it gets closer and closer to 0. Okay, so that's something to really take a look at. Okay, so here we have a couple of examples to kind of make an exponential function. So find an exponential function, f of x equals a b to the x, that passes through these 2 points. And let's round to 4 decimal places. So here's what we want to do. So we're going to use both points. So I'm going to use the point -2, 6, and I'm going to plug this into my function. I'm going to write it as y equals. So y equals ab to the power of x. So 6 is y, a I don't know, b I don't know, and x is -2. Alright. And then I'm going to do the same thing, but with 2, 1. So I'm going to plug it into y equals abx, plug in the 1 into the y, a, and then b is to the power of 2. Alright, and all I really need to do is solve for 1 and plug it into the other guy. So this is what I'm going to do. I'm going to solve for a. So another way that I can write this is 6 is equal to a over b squared. Because a negative, you can just put it to the bottom and it'll be a positive. So now I'm going to multiply both sides by b squared. This goes away, so we got a equals 6b squared. And now what I'm going to do is I'm going to plug it into the other guy. We got 1 is equal to a. So a, you can see that was 6b squared. Alright. And you get 1 is equal to 6b to the 4th power. So I'm going to divide by 6. So b to the 4th power equals 1/6. I'm going to take the 4th root to both sides. And remember, we also have to write plus or minus because it's an even root. So b is equal to plus or minus 1/6. Now, which one should it be? Should it be positive or negative? Well, remember, b is always a positive number. If we go back up, we said that the value of b is always a positive real number. Okay? Oops. Where was b? Yeah, b is always going to be positive based on these guys. So we're going to choose a positive value. So we're going to choose b is equal to positive square root of 1/6. And let me put that in the calculator. So 1 divided by square root of 6 is going to give me about 0.41. So that's what b was equal to. So now that I know what b is, I can plug it into a, which is this guy. So I'm going to have 6 times b, which is 0.41, squared is equal to a. So let's see what a is equal to. So a will be 6 times 0.41 squared. That's going to give me about 1.0086. So my function f of x is going to be equal to, we know what a is, 1.0086. We know what b is 0.41 to the power of x. And this will be my answer. Alright. Okay. Now let's do this example. This next example. So let's find an exponential function, f of x equals a to the x, so we don't have a b anymore. that passes through the point 2, 1 over 25. All right, so let's go ahead and write it as y equals a to the x. So we're going to plug in that value. So we know that y is going to be 1 over 25. And a, in this case, is going to be equal to 2. I'm sorry, it's going to be equal to 2. Now, we need to solve for a, so we're going to square root both sides. Plus or minus. So a is going to be equal to plus or minus 1/5. But notice that in this case, the one that has the x cannot be negative, so we're going to choose a positive. So a equals positive 1/5. So my function, f of x, is going to be 1/5 to the power of x. And that would be that answer.